In this video, we're going to do an AB Physics 1 FRQ. So we have spheres 1 and 2 have masses m1 and m2 respectively. Both spheres are suspended from the ceiling by strings of identical lengths. So sphere 2 is pulled back so that there is a tension in the string, and the center of sphere 2 is going to be a vertical distance h above the center of sphere 1 as shown in figure 1. So that's our height h. So then sphere 2 is released and then collides and sticks to sphere 1. So that means we have a perfectly inelastic collision, and the two spheres are going to continue to swing forward as shown in figure 2. They momentarily come to rest when their center of mass of the two spheres is at h center of mass right here, above the original height of sphere 1 as shown in figure 3. So we can see that it goes to an h center of mass that is higher than the original height that m2 was at. Now we need to think, if the mass of sphere 2 increased, does h center of mass increase, decrease, or remain the same? Well, we want to justify our answer. Well, clearly we can see the answer to this in the image. H center of mass is higher, but let's back up the reasons why. Well, we know that sphere 2 is going to be released from height h. So if you increase m2, that is going to give the moving sphere more momentum before the collision. And then after our collision, the spheres are sticking together. So then some of that mechanical energy is going to be lost because we have perfectly inelastic collisions. But the larger m2 is going to make the stuck together system move faster after the impact. So that means that the sphere will swing higher, and then the center of mass is going to reach a higher point here. Okay, so using conservation of energy and conservation of momentum, derive an expression for h center of mass in terms of m1, m2, and h using physical constants. Okay, so for part B, what we want to do is we're going to use conservation of energy because we're looking at the sphere 2 falling before the collision in our first stage. So before the collision, we have our kinetic energy is equal to 0 because sphere 2 starts from rest. Now after that, we have our gravitational potential energy relative to the collision height. So this is U initial, this m2 gh initial h. So then after the collision, when we are right here, we are going to have our gravitational potential energy UF equal to 0, and our kinetic final is equal to 1/2 m2 v squared. So then we have to write our energy equation, where we have kinetic energy initial plus U initial is equal to kinetic final plus U final. This is equal to 0, and then we have m2 gh here. This is 1/2 m2 v2 plus 0 here because that's 0. Because here we're going to say that our height is 0. So then after this, we can cancel out our m2, and we have our gh is equal to 1/2 v squared. After this, we multiply by 2 on both sides to cancel out that 2. We have 2gh is equal to v squared, and then v is equal to the root of that. That's 2gh. So then we can say that right before our collision, our sphere 2 has this speed. So we'll call that v2. Now, that is only for the first stage when we are looking at sphere 2 falls pre-collision. Now we have to look at our second stage, which is going to be when the collisions where the spheres stick. That was our perfectly inelastic collision. When you have your collision in this, we have our change in potential energy is still going to be conserved because our external impulse is going to be F delta T J, right? So then we have that it's going to happen over a very short time. So that means it's going to be negligible. So then we know sphere 1, it started at rest, right? And then we know that sphere 2 came in and hit it with a speed of 2gh. And then after, they stick together, and then they move with a speed v. Because now they're one object, so you have to look at m1 plus m2. So let's write this all out. So our initial momentum is equal to our final. We had our initial m1 v1 plus m2 v2, and we have m1 times 0 is equal to m2 times v2. So then we just get that this side cancels out. We have m2 times v2. Afterwards, we know that they stuck together. m1 plus m2 is going to be our combined mass. And they move together with a new mass. So then we just set these equal. Move this down here, move this down here. After this, we want to solve for v, right? So v is going to equal to m2 v2 divided by m1 plus m2. So then we can plug in our fact that v2 was equal to the root of 2gh right here where we have our expression for v2 right there. So then we have v is equal to m2 times the root of 2gh, all divided by m1 plus m2. So then we have a third stage where we have our combined spheres swing upward, right? That was that third stage. So then after the collision, we have mechanical energy conserved again. So then when we're at the very bottom, right after the collision, we have our initial kinetic energy is equal to 1/2 m1 plus m2 times that velocity squared, the new v. So then when we get to the highest point with that combined mass, we have the spheres stop again, and we have kf is equal to 0. So then we have the center of mass, it rose by h center of mass in this scenario. So then our potential energy is our mass, which is m1 plus m2 this time. And then we have our gravity, and then we have our center of mass height. So then we can use our conservation of energy. This is ui, initial final plus uf. So then at the bottom, right, we know that we're going to be at a height of 0. So then we have our 1/2 m1 v, or m1 plus m2 times v squared plus 0. This is 0 plus m1 plus m2 gh center of mass. So this was equal to 0 because we are going to stop our kinetic energy movement because we're all the way at the top, so all that energy is gravitational. It's at its max height. So then here we have that this was equal to 0 because we are at a height of u initial is equal to 0. So then after this, we can cancel out our m1 plus m2. So if we do that, we see that we have that on both sides. So then we get 1/2 the speed squared is equal to 2h center of mass. So we want to solve for that h center of mass. How do we do that? Well, we can divide both sides by g. So then we have that g there. So then here we have 1/2 v squared over g. So then after this, we need to cancel. Or no, we can just keep it like this. We've already solved for it. So then that's our h center of mass. Great. So what do we do with this? Well, if you remember earlier, we had h center of mass in our other equation. So we have in our other equation that was v squared is equal to m2 times the root of 2gh over m1 plus m2 squared. So then we can take this, and now that we have v squared, we can take that and substitute it in here. So actually you're substituting this equation into this one. So then we have h center of mass is equal to 1/2, or you can just write your v squared because you don't have to write that in one. So that's going to be m2 squared over times 2gh divided by m1 plus m2, all that squared, and all of this divided by 2g. So you can cancel out your 2g since that's in the numerator of both of your numerator and denominator. So you're left with m2 squared times h divided by m1 plus m2 squared. Because everything in your denominator just canceled out. You could also take your h and bring it out front, giving you h times m2, all divided by m1 plus m2, all of this squared. That's your h center of mass. Okay, now for our part C, we're asked, a group of students wants to create a collision where h center of mass is as small as possible. Describe the relative masses of sphere 1 and sphere 2 so that they create the smallest h center of mass. Justify your answer by using your derivation from part C. So if we want to have our h center of mass, we want to minimize this. This equation was your h m2 m1 plus m2 that we had earlier squared. So we know that that height is going to be fixed. So we need to minimize this. So that means we have to make m2 small, and then we want to make m1 large. So that means that the smallest H center of mass is going to be when we have our m1 much greater than our m2, because if m2 is really small and we divide by an increasingly large number, that is going to make the overall fraction smaller. And then that's going to make our H center of mass smaller once you square that smaller number and you multiply it by a fixed H. So the reason is because we have that our sphere 2 is going to be a moving sphere. But if it is much less massive relative to 1, then the sticky collision of the combined system is going to move slower. So it only rises a smaller height.